All right, so we're starting a new chapter, chapter 4, and this chapter is a very, very different topic than what we've talked about so far. We've hit set theory and symbolic logic so far, and even though those are two very different subjects in their own right, they do have some similarities, which we kind of saw with things like Venn diagrams and Euler diagrams, and kind of the way that we think about disjunctions and conjunctions with intersections and unions and all that kind of stuff. So this is a big departure from all of that. What we're looking at in chapter 4 is numeration systems, which are just the way that we symbolically represent numbers. Now, the first two sections of chapter 4, 4.1 and 4.2, we're going to be looking at ancient historical numeration systems. And we're not actually going to talk about every single one of them that's given in the book. So, for example, in 4.1, if you go into your book and you look at the systems that are presented there, there's actually three major ones. There's ancient Egyptian numeration, there is Roman numeration, ancient Roman numeration, and then there's Chinese numeration, or ancient Chinese. We're going to be talking about Egyptian and Roman numeration systems here, but we're not going to go through the Chinese numeration here. We're trying to keep this down to kind of a manageable number of systems. So again, what is a numeration system? It's just a way of representing symbolically numbers. You know, we've very much internalized the way that we represent numbers. But we probably, unless you've looked into it intentionally, you probably haven't thought too much about how that system of numeration has developed, where it came from. And it turns out the system of numeration that we use now, which is actually called the Hindu-Arabic system, is, in the grand scheme of things, not as old as you might think it is. It's been around for a while, but it actually took thousands of years of civilizations using numeration systems to get to the point where we have the way of representing numbers that we have today. There were lots of other primitive forms of numeration that preceded this, and that's what we kind of want to look at. So we're going to talk more about the Hindu-Arabic system starting in section 4.3. And just for reference, you know, to use some terms that we talk about when we usually talk about numeration systems, our numeration system is what's called a positional numeral system. And basically what that means, here's a number in Hindu-Arabic, 734, for example. Each digit in this number represents something different. This 4 here is in what we call the ones place. So this represents the number of ones in this number after considering these other symbols. 3 is in the tens place, so this represents 3 tens. 7 is in the hundreds place, this represents 7 hundreds. So each one represents groupings, which is something we talk about a lot in this chapter. Groupings of different numbers, ones, tens, and hundreds. And the position of those numerals tells us which one represents which. So that's what the positional part of this is referring to. Historically, it took a long time to develop a positional numeral system like this. We had lots of other forms before this. So let's think about the most primitive form of representing a number. What would you imagine is the most simple, I guess, form of keeping track of numbers or counting? Well, historically, it was finger counting. You know, on your body, you have 10 appendages that are perfectly suited for counting things. You have 10 fingers, right? Now, what was the purpose of counting or having a system for representing numbers originally? Well, one of the first needs for representing numbers, for being able to talk about numbers, was to keep track of livestock. So shepherds, ancient shepherds would use different systems to keep track of their sheep. You know, they want to make sure that they're not losing sheep to predators or runaways or things like that. They need to know at the end of the day that they have the same number of sheep or whatever the livestock happen to be that they started the day with. And, you know, ancient shepherds wouldn't have like 10,000 sheep in their flock. You know, so there wasn't really a need for a system that kept track of very large numbers at that time. And for that reason, more simplified, more primitive systems were perfectly sufficient for what they needed numbers for back then. So finger counting worked fine. However, you know, most shepherds would have more than 10 sheep in their flock. So what happens when you get to your 10th finger if you're counting? Well, this is where the system of grouping was kind of born. At least we believe it was. So imagine you're a shepherd and your sheep are in the field and you're trying to count them to make sure you have them all. And you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now you're out of fingers. What do you do for that 11th sheep? Well, what they would do is they would take a small stone or a rock or something and add it to a pile. And that stone or that rock would represent 10. So now that that stone is there, you can start over again counting on your fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you've reached 10 a second time. Put another rock in the pile. And those rocks are keeping track of the tens so that you can keep restarting the counting process on your fingers. That was the most primitive form of counting or keeping track of numbers that we are aware of, or that we believe. We believe that's where kind of numeration started. But there's other very primitive forms of keeping track of numbers that we've seen just by studying the past. And the simplest one outside of finger counting is a tally system. And both of these types of numeration follow something that we call one-to-one correspondence. So what we mean by one-to-one correspondence is that each one of these marks here represents one thing that you're counting. So I can match up each of these marks to each of the sheep that I'm counting, if that's what this number is representing. Here's what the number 13 would look like in tally marks, just single little lines. I have 13 of them. That's how I would represent the number 13. Now, I think most of us learn how to use tallies early on in childhood, preschool, kindergarten. We learn how to keep track of things using a system like this. And it doesn't take long for you to realize that this is a terrible way of representing numbers. Because if the numbers get very large, in fact, they don't have to get even that large, it's very difficult to look at a set of tallies and immediately know, oh, that's the number 13. You know, if I only have 4, 1, 2, 3, 4, I don't have to individually count those 1, 2, 3, 4. Oh, that's the number 4. I can look at that and my brain kind of sees 4 immediately. But when I look at this, my brain can't see 13 individual marks unless I actually count them. So it's very difficult for numbers much larger than, single-digit numbers to be represented by tallies in a useful way. And so this is where we introduce the concept of grouping. You probably remember doing this when you first learned how to do tallies. Rather than just put 13 lines right next to each other, every time we get to the 5th, or every time we count out 5, that 5th mark we use as a slash through the previous 4. And so what this does is it groups up tallies in groups of 5. And it's much easier to visualize that number with that grouping system. Our brains are much better suited for handling grouping than just this one-to-one correspondence here. So 5, 10, I have 2 groups of 5 and then 3 more. That's much more easy to tell that we're looking at the number 13. So that's an improvement on that tally system, but it's only a small improvement, because even then, if I want to represent a number like 749, that's a lot of groups of 5, and at that point I do have to individually count each of those little groups. So this still doesn't get us very far. So an improvement on that is a grouping system that uses powers of numbers, and this is where we get into something called a number, or the base of a number system. So again, if you think of our numeral system, 734, we have hundreds place, tens place, ones place. Well, the hundreds place, 100 is the same thing as 10 squared. And 10 is the same thing as 10 to the first power. And 1 is the same thing as 10 to the power of 0. If I wanted to use more place values, the thousands place, for example, is 10 to the power of 3. So every place value, and again, we talk more about this in section 4.3, but every place value represents a power of 10. Here are some of those powers of 10. 10 to the 0 is 1. 10 to the 1 is 10. And it keeps going. 10 to the 6, for example, is 1 million. We have a millions place in our numeral system. So using powers of 10 or powers of any number really is a much more efficient way of representing numbers. Why does 10 show up in our number system? Well, interestingly enough, we use things in groups of 10 or powers of 10 most likely because we have 10 fingers. And remember, that's where this whole system of numeration probably started, is with finger counting. There's a lot of evidence to support that because most historical numeration systems, not all, but most of them, use some form of grouping by powers of 10. Civilizations that never interacted with each other independently developed their own numeration systems that centered around this idea of groupings of 10. And the most logical explanation for that is because we have 10 fingers. So let me introduce the first ancient numeration system that we talk about in this section. It's Egyptian numeration. And the way Egyptian numeration works is we have sets of symbols. You probably know the term hieroglyphs or hieroglyphics, which are just symbols representing, written language or written numbers or something like that. We have this set of symbols representing different powers of 10. So there's a description of each one here, but a stroke or a vertical line is representative of the number 1. This looks like our intersection symbol from set theory, but they call that a heel bone. That's what they were thinking of it as. That's the number 10. This little squiggle is supposed to be a scroll. It's the number 100, and you notice we have these other symbols as well. Lotus flower for 1,000, pointing finger for 10,000, a burbot fish. To me, it looks like a happy little whale for 100,000, and then I like this one, an astonished person. It's a little guy throwing his arms up in the air. That's 1 million. Okay, so those symbols represent those powers of 10. But what if you want to write a number like, say, 300? Well, you would draw out 3 scrolls, 3 separate scrolls. So oftentimes we have these symbols written several times to represent different groupings of these powers of 10 here. So here's an example. I want to write this number in Hindu-Arabic form. And what I'm going to do is try to put my table here so you can kind of see what's what. Okay? So this is a number that could be written in Egyptian numeration. And notice again, we have those symbols, but they're being repeated. So let's start from the left. This is that astonished person that I was talking about. And you remember that represents the number 1 million. Okay? But there's 3 of them. So that means we're looking at a 3 million something. All right. Now, if you're thinking in terms of Hindu-Arabic, if I start in the millions place and I'm continuing to the right, what would the next place value be? Well, that would go down to the 100,000th place. But what symbol represents 100,000? It's that burbot fish or that happy little whale. We don't see any of those showing up here. So we need to put a 0 here to show that we don't have anything in that place value. The 0 is acting as a placeholder so that I can move on to the next place value. The next place value would be the 10,000th place, but the 10,000s, the symbol for 10,000 in Egyptian is that pointing finger, and I don't see any pointing fingers here. So that means that we have 0 of those groupings of 10,000. Okay? The next place value would be 1,000. Which is represented by that lotus flower. We do have those. 1, 2, 3, 4, 5 of them. So that means I have 5,000 in this number. Then we move on to the hundreds place. The scrolls represent 100, and I have 2 of them, so that's 200. The heel bones, those are my 10s, and that would be the next place value. I count 3 of those, so there's a 3 in my 10s place. And then the stroke, there's only 1 of those, that represents the 1s. And so this in Hindu-Arabic is the number 3,005,231, and you can see where you have to employ the use of those place values if you don't have a symbol for that place, okay, or for that grouping. So you'll want to have this chart handy, obviously, when you're working through these homework problems, because it's a whole new set of symbols that we have to learn. I want to do this in the other order. I have a number here. 204,358. It's in Hindu-Arabic, and I want to put this in Egyptian form. So we're going to sketch this number out using the symbols that we have here. 200,000. It's in the hundred thousands place. That little burbot fish is how we represent those. So now you get to see my pretty sad art skills at work. So give him a little happy face. A happy little whale guy. There you go. That one's not as happy. That's all right. There's a 0 in the 10,000s place, which would be the pointing finger. I'm not going to draw any of those because there's 0 of them. 4,000. That's the lotus flower, so I need 4 of those. So they kind of look like this. I need 4. 1, 2, 3, 4. Okay, next up we have 300. Fortunately for the hundreds, tens, and ones place, the symbols are a lot less, detailed, so you can draw them pretty quickly. 300, I need 3 scrolls for that. So that's going to look like, mine look like kind of curly question marks. Doesn't have to be perfect, right? And then what else do we have? 5 in the tens place. Those are the heel bones. 1, 2, 3, 4, 5. 8 in the ones place. Now I'm going to do something here. So sometimes when we have larger digits, that can correspond to a lot of those symbols that we're trying to write out. So sometimes we stack them. So rather than do 8 strokes all horizontally, which is actually okay to do, an alternative is to kind of stack them like this. And that keeps you from running out of, paper, basically. So this would be that number, 204,358. Okay? We want to do a little bit more than just representing numbers or interpreting numbers with Egyptian numerals. We also want to be able to add and subtract numbers. And that's very doable, and the system for doing that is very similar to what we do with adding or subtracting numbers in Hindu-Arabic form. With addition and subtraction, we do it vertically, and when necessary, we can either carry, which we'll look at what that looks like, or we do a sort of borrowing sort of system, okay? So notice how the addition here, all the symbols are lined up according to their types. I have strokes, heel bones, scrolls, lotus flowers, and remember, these are the ones places. Or these represent ones. How many do I have in total? 3, 6, 7, 8. I don't need a new symbol for that because 8 is less than 10, and we do things in groupings of 10. So I have 8 of these in total. 1, 2, 3, 4, 5, 6, 7, 8. How many heel bones do we have? 1, 2, 3, 4, 5, 6. I need 6 of those. 1, 2, 3, 4, 5, 6. How many scrolls do we have? These are the hundreds place. 1, 2, 3, 4, 5, plus another 6. That's 11. So we count that up first. And then notice that if we were doing addition with Hindu-Arabic and a column of numbers added up to 11, you would write a 1 down here and then carry the other 1 over into the next place value. Well, the one that goes down here represents whatever place value we're working with, which is hundreds. And because I'm carrying a 1, I need to only put 1 of these scrolls here. But then I'm supposed to carry a 1. And that 1 represents something different. It's being carried into a different place value. So instead of writing a 1, because we're not working with Hindu-Arabic numerals here, I would add another symbol that belongs to this category or this column. So this gets another lotus flower. And how many do I have? 1, 2, 3, 4, 5, 6. So down here, I draw 6 of these. These ones take a little bit longer than the other symbols. Halfway there. One more to go. Perfect. What number is this? 6,168. That's that number. I could always check my answer, which I'm not going to do here, but I could easily if I know how to convert these into Hindu Arabic form and then just add them up using the method I already know how to do. But this is how we would do this working exclusively in Egyptian form. Okay, let's try a subtraction problem. Subtraction is going to have a similar feel to how we'd normally do subtraction. So let's look at the strokes here. These are my ones places. I have 6 of them in this numeral, 3 of them in this one. So if I take 3 of these and subtract from 3 of these, I would have 3 remaining. 1, 2, 3. All right, no problem there. And sometimes what we do is kind of a canceling thing. I say I can cancel 1, 2, 3 of these guys with 1, 2, 3 of these guys, and I'm left with these 3. If I tried doing that here, I don't have enough of these heel bones up here, these 10s, to subtract the 7 heel bones that I have here. So how do we do that? Well, we use borrowing. Remember, each of these heel bones is worth 10. One of these scrolls is worth 100, which is the same as 10 tens. So I can borrow a scroll and convert it into 10 tens. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 heel bones. And now I can do some canceling. So again, I'm going to subtract 1, 2, 3, 4, 5, 6, 7 heel bones from 1, 2, 3, 4, 5, 6, 7 heel bones here. How many heel bones are left? 5, 6. 1, 2, 3, 4, 5, 6. That's what's left. Okay? Now I have 4 scrolls up here, which I have enough to subtract the 2 down here. That would leave me with 2. Okay. Finally, this lotus flower has nothing being subtracted from it, so it's just going to get carried straight down to the answer. What number is this? 4,263. Awesome. All right, one last thing I want to look at with Egyptian numeration, and this is, even though this is an Egyptian technique, we're going to do all of our work in Hindu Arabic. It's a very, very lengthy process if we want to use the Egyptian numerals here. And so this is more about the concept than it is the symbolic representation of things. Like I said up here, addition and subtraction, even though it's done with different symbols, it feels very similar to how we do addition and subtraction with our familiar system of Hindu Arabic numerals, borrowing and carrying, right? Multiplication, though, the way that the Egyptians did multiplication looks drastically different than the way that we do it in the way that we do it with our positional numeral system. And the technique I'm going to show you can be done in a few different formats, a few different ways. And I'm actually going to show you a way that's different from how the book shows. So it's equivalent, meaning both methods follow the same underlying. It's using the same underlying concept, but it's just going to look slightly different. So this system of multiplication goes by other names. Duplication and mediation is one term for it. Russian multiplication and peasant multiplication, because this was also used during the Russian Middle Ages by peasants working in the fields and things like that. So let's get to it. What we want to do is take the number 100. We want to do the multiplication 120 times 8. Okay. Actually, I'm going to change that because for reasons I'm aware of, and you wouldn't be quite yet. 8 is not a great number to illustrate this process. Let me do 120 times, let's make it 15. No, I don't want to do 15. I want to do, 120 times, let's make it 21. So, sorry, the reason I'm changing these numbers, the technique will work with either of these multiplication problems, but it doesn't quite illustrate it as well as other numbers. So what we're going to do is take the number 120 and the number 21, and we're going to put them into columns. And I'm going to intentionally put the smaller of those two numbers first. It doesn't matter which one goes where. I could put 120 here and I could put 21 here, but if you put the smaller number in the left column, the process is faster. That's really the only reason for doing that. Now what I'm going to do, separating them into columns, I'm going to take half of this number. Now what is half of 21? Well, half of 21 is 10.5 or 10.5. And I'm going to just get rid of the decimal part of that. So 10.5, if I ditch the 0.5, I'm just left with 10. Then I'm going to take half of that. Half of 10 is 5. Then I'm going to take half of that. What's half of 5? 2.5. But as before, if you get a decimal, you just chop that off. Leaves me with 2. And then I cut that in half, which gives me 1. Okay, now I've gotten down to 1, that's where I stop. In my other column, I'm going to do the opposite of taking half of something. I'm going to multiply by 2, or I'm going to double this. So if I double 120, I get 240. If I double 240, I get 480. If I double 480, I get 960. And if I double 960, I get 1920. Okay? Now, notice things line up here, right? I have kind of rows that I've created. And what I'm going to do is go through my left column and look for only the odd numbers. 21, 5, and 1. Those are the only odd numbers that appear in this column. Next to the odd numbers, I'm going to circle the corresponding numbers in this row, or this column, sorry. So I'm only using the numbers that are adjacent to odd numbers. I don't use anything adjacent to an even number. Then what I'm going to do is take those 3 numbers that I circled and I'm going to add them together. 1,920 plus 480 plus 120. What would this be? So I'm adding zeros, that's 0. 10 plus 2 is 12. Carry the 1. This adds up to 15. 2,520. This is the answer to that multiplication problem, believe it or not. It seems like an incredibly bizarre way to do multiplication, and it seems like it would be inexact also, since it appears that I'm not using exact answers here. When I took half of 21, I didn't write 10.5, I wrote 10, right? Yet, this will always give you a correct answer to whatever multiplication problem you're doing it on. Even if I switched the columns, if I put 120 here and took half of that, and if I put 21 over here and doubled that, and did the same process, I would still get 2,520. Why does this technique work? Well, I can show you, but it's going to be easier if I show you after we talk about some of the things that come up at the end of this chapter, namely number bases. This is an application of the binary numeral system, which we will talk about, but later. So I may give like a little explanation as to how this works once we've covered that material. But for now, you can just kind of be in awe of this bizarre technique that always works. Obviously, this is not a good way to do multiplication for practical purposes. It's much, much faster to use the techniques that we learn in elementary school, if you're not using a calculator. But this is not intended to be a fast or efficient way of doing multiplication. Remember, this is an ancient form of multiplication. It came before we had more efficient methods. All right, so I'm going to end this video here, and in the next video, we'll talk about the Roman numeration system.